Right. Next. So that is dye in photochemistry. So singlet reactions are different over triplet reaction. Always answer depends upon triplet sensitizer ET1 value. Okay. So take one example. I am giving one dye in, give the product for that. Here it is a dye in photochemical direct. If they not mention, it is direct. So then what happens, is it cis olefin or trans? Cis. Cis means you may expect a electrocyclation here. That is the answer. Okay. Next. Here hydrogen. Here two double bonds I am writing, same. Photochemical direct. What is the answer? So these two will be combined together like this. Your answer remains same. Double bond, double bond. One will be disappear out. This will be as it is, dotted line, and here it will be. Now here also remains same. Now trans partner. It is not cis partner. It is a trans partner. See, this is a trans partner. When trans partner combine, what is your answer? Bicyclic compound. So this will combine with this. This will combine with this. Is it trans or not? Trans directly irradiated, you will get a bicyclic compound. So that is 1,3 butadiene. Next, keep heading photochemistry of 1,4 diene, unconjugate dienes. So it is also called dipymethane. Dipymethane or Zimmermann rearrangement. So two names are there, dipymethane rearrangement or Zimmermann rearrangement, or photochemistry of 1,4 diene. Both are same. Photochemistry of 1,4 diene, also called dipymethane rearrangement or Zimmermann rearrangement. Okay. So here this is a dipi. Photochemically I am irradiating. Photochemically I am irradiating. Dioxane is a solvent. So here you may expect a vinyl cyclopropane. If I take any aromatic ring and here double bond photochemically, so same cyclopropane attaches to aromatic ring, aryl cyclopropane. Suppose if I take berylline, this is called berylline. Berylline. So photochemical irradiation. So here you may expect a 5-membered ring and here 5-membered ring. This is the answer. Okay. So these all are called dipymethane rearrangement. Dipi. Here 1, 2, 3, 4 and this is 5. Total how many? 5 carbons are there. First carbon having double bond, fourth carbon having double bond. That's why 1, 4 diene. So in middle CH2 is there. CH2. CH2 separated by 2 double bond. Okay. Left side 1 double bond, right side. See, CH2 left side 1 double bond, right side 1 double bond. Here also 2 double bonds separated by 1 carbon. 2 double bonds separated by 1 carbon. If 2 double bonds are separated by 1 saturated carbon, that is called dipymethane. So what is methane? Methane generally you will write like this or not? It is CH4. CH4 is called methane. Suppose if 2 hydrogens are replaced by double bonds. Here left side 1 double bond, right side 1 double bond I written. So this is called dipymethane. See, CH2 and 2 hydrogen. Is it CH4? CH4, CH4. Right side hydrogen replaced by this one. Left side hydrogen also replaced by double bond. So dipymethane. Dipymethane. Clear? It is almost all equal to structure of methane only, but 2 hydrogens of methane replaced by 2 double bond. That's why dipymethane. Right. This is semi-bulbulin and this is called berylline. Berylline converts into semi-bulbulin. Photochemical dipymethane rearrangement, also called Zimmermann. Z-I-M-M-E-R-M-A-N-N. Zimmermann rearrangement. Here you write rearrangement of 1, 4 diene into vinyl cyclopropane or aryl cyclopropane. It may be vinyl or aryl cyclopropane in light. Here I am using photochemically. Is dipymethane rearrangement. Dipymethane or Zimmermann rearrangement. Zimmermann rearrangement, dipymethane, both are same. So if I take 1, 4 diene, that will give vinyl cyclopropane. This is called vinyl cyclopropane. And what is this? Aryl cyclopropane. Here right side group is vinyl. This is vinyl and this is cyclopropane. This is aryl. Aryl cyclopropane. Formation of vinyl cyclopropane and aryl cyclopropane. Rearrangement of 1, 4 diene into vinyl cyclopropane or aryl cyclopropane is called dipymethane rearrangement. Light should be taken and that is also called Zimmermann rearrangements. Write characteristics. C. Reaction exit state is pi 2 pi star singlet and pi 2 pi star triplet. Both are possible. Okay. So this is liquid state reaction. It is not gaseous state reaction, liquid state reaction. Both acyclic and cyclic molecules are involved. Acyclic, cyclic 1, 4 dienes are involved. Open chain diene and cyclic diene both are involved in dipymethane rearrangement. Reaction exit state is pi 2 pi star direct, it is indirect. Required a triplet sensitizer for triplet. For pi 2 pi star, triplet sensitizer required. But answer remains same. Answer will be remain same. Liquid state reaction, aqueous state or complete liquid state or solution state reaction, acyclic molecule, even cyclic molecule can involve. Acyclic, cyclic molecule both involve in Zimmermann rearrangement. So in this one, intermediates are cyclopropyl 1,4 biradical. Cyclopropyl 1,4 biradical. And especially see, it is a regio and stereo selective reaction. Regio and stereo specific reaction. Regio specific or stereo specific. See, unstable radical, part of unsaturation, unstable radical, part of unsaturation, and stable radical, part of cyclic ring. So this point is a shortcut. This is only shortcut for you. So now you will get 1,4 biradical or not? You will get a 1,4 biradical. After getting 1,4 biradical, if the two radicals are unstable, whichever is unstable, that unstable will be part of double bond. Unstable radical, part of unsaturation, double bond. Stable radical, part of ring. You will understand by taking mechanism, but right now you remember this statement. Intermediate is cyclopropyl 1,4 biradical, regio and stereo specific reaction, unstable radical part of double bond, stable radical part of cyclic ring. Stable should be part of cyclic ring. So if you see the mechanism, I am taking a dipi, it is photochemically excited S0 to S1. After S1, remember, two inner radicals we need to join together. So first two inner radical, two inside radicals you need to join together. When you join these two radicals, you will get a ring. This is called cyclopropyl 1,4 biradical. Two inner radical, this inside you need to join. So you will get a joining point here, 1, 2, 3, 4. This is called cyclopropyl 1,4 biradical. From there onwards, your answer will decide. Okay? So after getting this intermediate, now see, I am breaking towards right side. This is A side. Suppose if I break this side, then what happens? This radical forms. This radical, there is a double bond or not? Now already where bond is present, here bond is present. Now this carbon attaches to here one radical, here one more radical is there. Okay, later on these two will join together. That is the answer. Suppose if I break left side, B, direction B side. So if I break here, now this radical, double bond, and you will get this. Here two carbons are present. This radical as it is, this radical as it is. Now these two will join together now. So it is direction B, direction A. Now this can I write like this directly, double bond. Here C. This is one. And this molecule also I can write like this. Here double bond. Here you write double bond. And this is connected to this. And here this is the answer. Every time remember, if you give numbering, see always start with saturated carbon. 1. Okay. This is shortcut I am giving. 1. Suppose between these two, whichever is unstable, that you need to write on double bond side. See, this is double bond. Here double bond. Here also we are getting double bond. After getting biradical, here this breakage will decide the answer. Which side you are breaking? Suppose if you are breaking right side, this radical, double bond. So try to break that side where you will get unstable radical. Suppose see this is unstable radical. This is stable radical. Unstable radical means here we need to break. If you break here, this and this, what? Double bond. So unstable radical part of the double bond or not? That is the statement. Unstable radical part of unsaturation. That is double bond. So now this is stable or not? Suppose assume that it is stable. So if it is stable, stable radical part of ring. Stable radical part of ring. So this is part of ring. This and this join together. So always remember whichever is stable, that becomes 1, 2, 3. Join 1 and 3. Join 1 and 3, 2 connected to inner carbon. Whichever is unstable, that is double bond. Clear? Unstable radical is part of the unsaturation and stable radical is cyclic. Ring carbon. It is stable. Suppose right side is unstable. We need to break right side only. Now between these two radical, which is more stable? Both are same. Both are same. We can't give priority for right side or left side. Suppose if right side is unstable, if I give any new molecule, if right side is unstable, on that time we need to break right side. This side we need to break. If you break here, this radical, double bond, this radical ring. Which means stable radical part of ring, unstable radical part of double bond. Right. So what is radical stability order? What is radical stability order? Benzyl is more stable than allyl. Allyl more stable than tertiary, secondary, primary. It is radical stability order. Radical stability order. Benzyl radical is more stable than allyl, allyl more stable than secondary, tertiary, secondary and primary. Second one, a double bond, photochemically activated. Now it is reaches to singlet state. S0 reaches to S1. Now 1, 2, 3, 4. You focus on this 4 radical. Join inner radical. First point is join inner radical. If I join inner radical, what is your answer? Double bond. First you write down this as it is. Write down 4 electron. If I write 4 electron, join inner radical. First you join these 2. After joining, leave these 2. Right? Is it 1, 4? Yes. Up to here, no problem. First you create up to here. Then later on, which side you need to break? That is the question. If you know that point, answer is over. Now before that, you need to know which radical is unstable. That side we need to break. Corresponding 3 membered we need to break. See, between left side radical, right side radical, which radical is unstable? Guess. Which is unstable? Right side or left side? Right side. Right side is stable, left side is unstable. Not right side. Left side is unstable. Why? Left side, I am breaking left side because this is initially aromatic or not? After combining two inner radical, you are getting non-aromaticity. Stable to unstable or unstable to stable? Stable to unstable. Unstable molecule want to attain aromaticity. So that's why I want to break here only. So if I break left side, see what is your answer. If I break here, now can I, after breaking here you will get one radical and here also one radical, right? This radical join together and forms, what is your answer? Double bond, double bond, double bond, right? Now here you will get a radical or not? Now this molecule finally I can write like this or not? Can I join these two? I am going to join these two. So finally your answer is, after joining these two, write one carbon, write 3 membered. Aryl cyclopropane. Now what is the shortcut? Shortcut is C. Here this is a double bond formed or not? Is it unstable radical? Is it stable or unstable? This is unstable radical. Then what about this radical? It is a stable radical. It is a stable radical. It is an unstable radical. Whichever is unstable, adjacent 3 membered we need to break. Whichever is unstable, that side we need to break. And this become a unstable radical is a part of. Unstable radical is a part of unsaturation. Stable radical is a part of ring. See, this is a stable radical or not? Stable radical now present in a ring or not? Unstable radical present in a double bond. That is that statement. If you know this point, answer is over. Okay? Unstable radical is part of unsaturation. Don't break this bond. If you break this bond, you will get original structure only. This one you will get. Here how many breakages possible? 2 breakages. Right side, left side, both are possible. I am breaking left side. Why I am breaking left side? Because initially molecule loses aromaticity. If I break this side, molecule very fastly attain aromaticity. If they attain aromaticity, it will get this product. So, I am saying this radical unstable. Unstable radical adjacent ring carbon should be broken. And this radical forms double bond. Here I am breaking, that's why this radical join together and forms 3 membered. So, it is a stable radical, unstable part of double bond, stable part of ring. Clear? So write the answer for this. Here double bond and here I am writing 1 methyl. So photochemical, what is the answer? Dipyromethane. Give the answer. Whichever side first unstable come, that you introduce in double bond. Whichever stable radical comes, that side you give numbering 1, 2, 3. Join 1 and 3, 2 and unsaturated inner carbon, you will get double bond. Just imagine like this every time. See, remove this double bond in your mind, remove this. Like this you need to imagine. I remove this two double bond and these two corners you need to focus. Here one radical, here one radical. Which is more stable? Like that in your mind you need to think. Remove the two double bonds, put two radicals here. Which is more stable? Between right side, left side, which is more stable? Left side is more stable. It is secondary, it is primary. Secondary more stable means left side is stable. Left side you write down 1, 2, 3. Okay? So, this 2 and this double bond you write down as it is. This 1 and 3 you need to join. That is the answer. Whichever is unstable, that is part of the ring. Now, which is unstable between left and right? Which is unstable? Right side. Right side means this and this you join together and put double bond. And here 1, 3. 1, 3, ring. This you write down as 1, 2, 3. A normal numbering, not IPAC numbering. For your understanding purpose, I am writing this. Join 1 and 3. Join these two over here. Now which is more stable? Left or right? Right is more stable. Benzyl. So 1, 2, 3. Now 1 and 2 you write double bond as it is. You join this 1 and 3. What about this? Left side is stable, 1, 2, 3. So join this 2 and double bond as it is. 2 join with this, break this bond. This 1 join to 3. Which is stable here? Right side is stable. Right side is stable. Write down 1, 2, 3. So after writing 1, 2, 3, so how to predict answer? This right double bond as it is you write down wherever you are not giving numbering. So join this 2 and double bond. This 2 carry 1, 1 attaches to 3, this 3 carry phenyl methyl. If you don't know shortcuts, impossible to predict the answer. Otherwise, if you write mechanism, it will take much more time. Now between these two, which is more stable? Right side or not? Right side more stable. Right side more stable means you need to new numbering 1, 2, 3. So after giving 1, 2, 3, left side double bond write down as it is by breaking this bond. These two join here. 2 connected to 1. This one having how many methyls? 2 methyls. 1 connected to 3. 3 having phenyl. Then this 3 connected to 2. Give this answer. Below CH2 is there. Here above CH is there. Now CH2, C and here C. This is dipymethane, not this side. Below is there. Here dipy given like this. In this model, you need to assume like this dipy. I given like this. Reverse I given. Dipy methane. Below methane is there. See, first you need to combine these two. Methyl, 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 and here 2 methyl, here radical, radical. You should combine like this. Cyclopropane. These two inner join together. Now after this, break this. Any side you can break. Both are same. Break this. After breaking this radical, a double bond. Here methyl and this is methyl. So here one radical is there. This radical I am writing this carbon here and writing this side. Any? This carbon I am writing like this. So now these two radicals combine together and forms 3-membered ring. Here remain same. Write down 5 membered, 2 phenyls, and here double bond. Right side, left side I am breaking. Right side you will get 3 membered, and this is pH. So this carbon is this one. Now, so which is unstable here between left and right? Left is unstable. So when left is unstable, left you should write as it is. Here this is methyl, and this part will be as it is. pH and pH. Now these two join together. Here this pH like this. I am breaking left side. This carbon I joined here. So here 1, 2, 3. Here almost all same answer. So if I write 5 membered ring, double bond and methyl, and here pH, 2 methyls. Here methyl and here methyl. So this 4 you take down as homework, work out later. So to identify where 1, 4 dipi is present. If you identify that, your answer is over. See, this is methane, CH2, CH2, CH or C. It may carry 2 hydrogens or it may carry 1 hydrogen or no hydrogen. Saturated carbon, left right double bond is present. So these two are inner. First you join these two. Inner you need to join. Then break right side or left side wherever you get aromaticity. If aromatic ring is there, always try to attain aromaticity. You work out that. First inner carbons. See, double bond, saturate, double bond, right? Double bond, saturate, double bond. Means inner carbon we need to join together. Means this carbon we need to join. You need to put a single bond here. Is this radical 1, 4 or no? Between above radical, below radical, which is unstable? Above. So this double bond will be as it is. So here a new bond formation takes place. This is the answer. Clear? First what happens, see, these two radicals join together. Here 1, 4 biradical you will get. This carry methyl and this is CH3. Is it clear? Intermediate 1, 4 biradical. 1, 2, 3, 4. So between above and below which is unstable? Above. Above unstable means whatever new bond we created we should not break this one. Break this one. If I break here this radical, double bond. See this. So this bond is as it is. Here you will get double bond and this is methyl. And here you will get one radical. This is CH3 dotted line. And here one phenyl, this one. So these two radicals will join together. If these two join together, you will get this one. That is CSR question. Clear? Next, in that only oxidipymethane. Oxidipymethane rearrangement. Oxidipymethane rearrangement. Now dipi is over, next oxadipi. See, beta gamma unsaturated carbonyl compounds. Beta gamma unsaturated carbonyl compounds converted to cyclopropyl carbonyl compounds. Carbonyl compounds in presence of light. So in presence of light, this reaction possible. This is most important as compared to dipymethane. As compared to dipymethane, this is most important. If this is given, definitely they will give one more interconversion with Narish one. Last year also one question came from here. This one and Narish one little bit confused. So only structure can help you. So what I given? This is, see, if I put a double bond here, if I put a double bond and if I put one more double bond, what is this? Dipymethane or not? Suppose if I put carbonyl group, that is called oxidipy. One is double bond, other is carbonyl group. This is alpha, beta, gamma. Now photochemical I am using. Here acetone is a common solvent for this. Acetone is a common solvent. Now remember the shortcut. First you break bond between alpha and carbonyl carbon. Okay, if I break bond between alpha and carbonyl carbon, see, alpha and carbonyl carbon I am breaking bond. First you write down like this. Right? This bond I am breaking. Alpha carbonyl bond you need to break. Remove this double bond. Join carbonyl carbon and beta. Join carbonyl carbon and beta. Join beta and gamma. That is the answer. Means it is looks like same. Approximately same. This is carbonyl and this is cyclopropyl. Shortcut is, remember, see, first you break bond between alpha and carbonyl. Join alpha gamma, join beta carbonyl. Join these two, join these two. This technique can help without any mistake, you can write the answer. Join alpha gamma, join beta carbonyl. And before that, first you need to break bond between which one? Alpha and carbonyl. Just listen, don't write. So will you give the products for this? This is carbonyl, double bond. Here carbonyl I am writing, this is methyl. Then photochemically, what is the answer? First give labeling, alpha, beta, gamma. First you break bond between alpha and carbonyl. Write down this carbonyl without bond. Then this and this you join together. Okay? After joining beta, alpha, gamma, write this. This beta carry methyl over. Join alpha and gamma. Join alpha and gamma, you will get the answer. Just listen. One more example I will give. See, this is methyl and here I am writing phenyl and methyl. Photochemical, what is your answer? See this. Alpha, what is this? Beta, gamma. First. Join, first you write down carbonyl as it is. Whatever substitution is it, that you write down as it is. First you break this bond. Join this one and beta. Beta carry alpha. Alpha connected to gamma. Write this. It is alpha. Alpha having phenyl and methyl. Then gamma carry methyl. That is the answer. Very easy. So this is a question which is given in exam. Just give the answer. Here double bond and they given C double bond. That is a question which is given. CSR 2024 in CSR exam, this is given. Right side Narish 1 they given, left side oxidipymethane they given. As compared to dipi, oxidipy very easy and most important. When this is given, think about Narish 1. Even Narish 1 and this answer remains same. Apply the technique what I given, you will get the answer. See, first you write down alpha, beta, gamma. Right? Break bond at alpha and carbonyl. First you remove this bond. So after removing this bond, first see, you will get this. First you write like this, skeleton as it is. Remove this bond and double bond. Join carbonyl carbon and beta. Can I? Then this carbon put ring. That is the answer. Generally you will write like this and you don't know what to do. How to write this? See. So you will join this, same answer. But in exam they won't give like this. They will give convenient structure. Gamma to beta or not? Gamma to beta, that's it. This is initially carbonyl carbon, beta, carbonyl carbon, beta. Then gamma joins with alpha. So this alpha I written conveniently like this. You practice like this, then conveniently you write down like this. So these three molecules are given in exam, just you try this. Here I am writing phenyl. This is C double bond O Me. This is acetone. Give the answer. This now upcoming three molecules are repeated in GATE and CSR exam. You should be very strong. How to write? This is last year given. Last year given. Check your. Suppose if you have any papers, you can check. I will give in practice questions. I will give this one. But remember, you need to identify what kind of reaction it is. Nourish 1, nourish 2, everything is over. On the time impossible to identify nourish 1 or dipymethane. Dipymethane, oxidipymethane. If anybody says the oxidipymethane, then you can write the answer. That is a problem with photochemistry. Now, see, carbonyl group is there or not? What is this? Alpha. What is this? Beta. Then gamma. What is the shortcut? First we need to break bond between alpha and carbonyl. Then we need to join alpha and gamma or not? Alpha and gamma. See, first I am breaking this bond. I am breaking carbonyl and alpha. Then this alpha and gamma join together. Then beta carry carbonyl group. Is it right? If you want to write mechanism, you won't get the answer. Open chain is different, rings are different. That's why I am saying apply shortcut. Without hesitation, even if you know mechanism, even if you write mechanism, you will confuse. If you apply shortcut, your answer is clear. See, I am writing carbonyl on which carbon? Beta. I am breaking bond at alpha and carbonyl. This carbon I written here, this and this I joined. Here also same. See, I broke in here. This carbon I joined on beta. I joined on beta. Here also this carbon I joined on beta. So don't think, sir, I want to join from like this. So you will think like this. That's why you are confusing. So here carbonyl is initially present here. Right? Initially carbonyl group is present here. It is connected here. It is connected here. Break bond between alpha and carbonyl. Join carbonyl, carbon and beta. Join alpha and gamma. Over. Simple. So this is also given in CSR 2024. Last year. These two they given. Left side, right side. Questions they given. I will show that question. Now give photochemical product of this one. Oxidipy. What is the starting material involved in oxidipymethane? Beta, gamma, unsaturated carbonyls. that is responsible to give cyclopropyl carbonyl compound. You need to attempt with your hand, then only you will get clarity. Like that, if you want to write very freely means it is not easy. Your hand will not move. Even simple examples you can't write easily. Apply shortcut. Learn mechanism but don't apply mechanism for writing any answer. Apply shortcut. That shortcut you need to remember very fastly. Shortcuts will give clear answer without any mistake. Otherwise, if you want to write mechanism, you can write mechanism and you can pick the answer. Is it alpha? Here beta, gamma. Where should I break? Alpha and carbonyl. First you break this, remove this bond. So after removing bond between, first remove bond between alpha carbon and carbonyl. Then remove double bond. First you remove these two bonds. Remove carbonyl carbon and alpha bond. First you remove this, I removed. Then remove double bond. Then joining, simple joining. Join beta and carbonyl. Join beta and carbonyl, join alpha and gamma. Over. So this is a question which is also given in exam. Even in GATE also it is repeated. Photochemical acetone. So I am changing the positions of substitutions. These are asked in variable entrances such as CET and NET exams. They are also important molecule. They are changing the positions and they are asking. But concept is remains same. Reference molecule is this one. Now give labeling. Can I say is it alpha? Then what is this? Beta, gamma. What is shortcut? First remove bond between alpha and carbonyl. Remove double bond. Then join alpha and gamma or not? Alpha, gamma joining, this and this joining. Right? Now this molecule they won't give like this. So is it exist? This and this both are same? They will give like this. In your examination, in options, if it is appeared here, if this molecule is appeared anywhere, like benzoylene, it is looks like a benzoylene, not benzoylene. Benzoylene is a 5-membered. If I put one bond over here, that is called benzoylene. Looks like benzoylene. This is called benzoylene. This is benzoylene and this is called fulvene. It will comes in photochemistry of benzene. Benzoylene, fulvene. See, it is looks like same or not. This part is remains same. Benzoylene. If this is appeared anywhere, starting molecule is 5-membered and 4-membered. Now, give the answer for this. Like this you need to write. That's why positions they are asking. First you write 6-membered, then you write carbonyl here, then you write like this, then where should I write methyl and phenyl? That is the question. So can I write phenyl here? Say yes or no. Over here. Or above can I write? Can I write above? Or you don't know? See, writing normal molecule very easy. But definitely they will target substitutions. I given shortcut. I given mechanism, I given shortcut still. But if substitutions are given, where we need to decide. See, carbonyl joining here. This point is this. This is joining here. So, carbonyl to this is alpha. This is alpha. Next one. Actually that carbon belongs to beta from here. If I take this is beta, now this is beta. But initially it is beta, right now it is alpha or not. This carbon, next is this. Tertiary carbon. Is this two or same? Same or not? Here I written, this carbon I am assuming as this one. This carbon I am assuming as this one. Otherwise, you can take this carbon as this carbon as this. Both are same. Any one is possible. So, this carbon initially what? Alpha. Now, alpha carbon may be any one of this. Now, alpha carbon having methyl. So, I can write this methyl here. Can I? Can I write methyl here? Above. Or can I write on above carbon? Any carbon you can write, your answer remains same. Then what next? This carbon attaches to which one? Phenyl. So is it phenyl here or not? This is phenyl. I think this is better than that example, I think so. Normally in CSR, a typical molecule they will ask. In set exam, net exams, what they are doing is, they are not asking typical molecule. Whatever CSR questions they are given, slight changes they are giving and they are asking. Only identification. If you identified clearly, 4 marks will be in your hands. Now, can I write this? Same 6 member I am writing, C double bond O. You can write here. Now, this is below I am writing. This carbon, can I write above carbon or below carbon? Anywhere you can write. Here this is pH. Then what about this? This is methane. Right? Where you will write. Now this carbon attaches to this one or not? Is it initially alpha or beta? Beta. Beta carbon joined to carbonyl. Beta carbon joined to carbonyl. So here I can write phenyl. Next, where you will write this one? You can write either here or here, anywhere you can write. This carbon, both are same. So then you write down methyl over here. Here or here, both are same. These two positions are remain same. So that is end of oxo-dipymethane rearrangement. So today class we discussed about diene photochemistry, then dipymethane photochemistry, then oxo-dipymethane photochemistry. Oxo-dipi and 1,3 butadiene is most important, and even dipymethane also important only for interconversion. But you can expect a straightforward question from butane, 1,3 butane, singlet reaction, triplet reaction, and dipymethane, oxo-dipymethane. Out of these two, oxo-dipymethane is most important. While revising oxo-dipymethane, you can also try to prepare Nourish 1. Nourish 1 oxo-dipymethane questions are coming. Clear? So we'll stop here. So next is photochemistry of benzene. Photochemistry of olefin is over. Photochemistry of conjugate olefins still I completed. Then the photochemistry of conjugate olefins related to unconjugate olefin, that is called Zimmermann rearrangement. Then later on oxo-dipymethane rearrangement, it is almost all equal to dipi, that's why I explained in dipymethane rearrangement only. Okay, I think as compared to dipymethane, oxo-dipi is very easy. Why? Can you guess? Oxo-dipymethane is very easy as compared to dipymethane. In dipymethane we need to see which is stable radical, which is unstable radical. But here there is no such type of problems. Only thing is directly every time carbonyl compound. In this also 1,4 biradical, same mechanism. That's why not given mechanism. In place of carbonyl right side, what is present? Here right side double bond is there. Here what I written? Carbonyl. So what is intermediate? Suppose if double bond is present, what is intermediate here? Two double bonds are present. These are the intermediates or not? Suppose if carbonyl is present, what is intermediate? Oxygen with this. Now wherever oxygen carry radical, that is found to be unstable. So If it is unstable, break this bond and write double bond here, join these two. That is the answer. Whichever side carbonyl group is present, that carbonyl always, one more time, get back to carbonyl, alpha carbon becomes a cyclopropane. Clear? So this last 4 to 5 examples are most important for CSR examination. Okay, we'll stop here and we'll continue tomorrow morning. Tomorrow morning same timing. Evening schedule will be announced in your WhatsApp group. We'll stop here.